Hi everyone. First off, I know Matt Parker of the channel Stand Up Maths just made a video about derivatives, and you should definitely go check that out too if you find this interesting. But I have been planning this since before that was posted, and it has some different stuff from his, so I'm still putting this out there. Secondly, I'm making this video for 3 Blue 1 Brown's math contest, Summer of Math Exposition 3, so shout out to him for hosting the contest. Without further ado, let's begin. If you've never taken calculus, don't worry, I'll give some background for this video. If you know what a derivative is and you're comfortable with the power rule, you can skip to the time on the screen right now. If not, I'll explain as simply as possible. First, some notation. The derivative of f of x can either be written as d over dx f of x or f prime of x, and I'll be using these interchangeably. Alright, here's a function f of x equals x squared. The blue line is called a tangent line because it only hits the curve at one point. Now, the derivative of any function is a function that gives the slope of these tangent lines on every point of the function. This particular tangent line has a slope of 3, so we know that the point 1.5, 3 will be on our derivative. I won't go over how all derivatives are found, but a rule you learn early on in calculus is the power rule. The derivative of x to the n is n times x to the n minus 1. Also, the constant multiple rule says that the derivative of any function multiplied by a constant is also multiplied by that constant. So the derivative of x squared is 2x, and the derivative of 2x squared is 4x. We're going to be looking at two starting functions, x to the 10 over 10 factorial and sine of x. Just a reminder, factorial is represented by an exclamation point, and n factorial means to multiply n by n minus 1 by n minus 2 all the way down to 1. So for example, 5 factorial equals 5 times 4 times 3 times 2 times 1. The reason we're using this first function is because the derivative of x to the n over n factorial is x to the n minus 1 over n minus 1 factorial. Think about it with an example. If you have the function y equals x to the 6th over 6 factorial and you use the power rule and the constant multiple rule to take its derivative, you will get y equals 6x to the 5th over 6 factorial. Dividing the numerator and denominator by 6, we get y equals x to the 5th over 5 factorial. We're going through 10 derivatives, and the 10th derivative of x to the 10 over 10 factorial is 1. The reason I'm using sine of x as our second function is that its derivatives are cyclical. The derivatives of sine of x go through a cycle, with its fourth derivative being itself, and with each derivative looking like the same wave moved to the left. It is therefore useful for showing geometric properties of derivatives, like what their x-intercepts imply for the original function. I will also be showing discontinuities in each derivative using the function e to the x, whose derivative is itself, and a series called the Taylor series. A Taylor series is an infinite series which can approximate a non-polynomial function with a polynomial by adding arbitrarily many terms. This is done by matching each term to a derivative of the function. Our Taylor series will be centered at x equals 2, so the first term will have the same value of e to the x at x equals 2. The first two terms will share a first derivative with e to the x at x equals 2, and so on. I will also make this a piecewise function, so before x equals 2 I will use the Taylor series, and after x equals 2 I will use the function e to the x. Each time I add a term, we will be viewing a discontinuity in a higher derivative. The first term will be discontinuous in the first derivative, the first two terms will be discontinuous in the second derivative, and so on. Now, in physics, functions are often used to describe motion. For the sake of simplicity, our original function will represent position, which is sometimes known as displacement. The x value will give time, and the y value will give the position of a particle along the number line, commonly given in meters. When we take derivatives, we say we are differentiating with respect to x, or with respect to time. If the particle's position, or y value, is negative, this means the function is below the x-axis. We can imagine it to the left of 0 on our imaginary number line. Here is a particle moving according to our first function as time goes from 0 to 10 seconds. Its position is never negative, as raising something to an even power like 10 will always yield a positive answer. Here is a similar animation for sine of x. Finally, here is motion according to a discontinuous function. So, if our original functions give position at some time, what do their derivatives show? For each derivative, I will show the original function as a dotted line in the background. Here's the first derivative of x to the 10th over 10 factorial, x to the 9th over 9 factorial. You can see that this function is negative when x is less than 0, as x to the 10th over 10 factorial is decreasing when x is less than 0. This function also increases faster than x to the 10th over 10 factorial, showing that the slope of x to the 10th over 10 factorial increases faster than the function itself. We will see a similar pattern through these derivatives, with every other function being negative when x is less than 0, and each derivative being closer to the y-axis than the last when closer to 0, but less so when further. I won't say much about each derivative, but it's interesting to get to see them generally get closer and closer to the y-axis and more spread out. Here's the first derivative of sine x, cosine x. The relationship between sine, cosine, and negative cosine are good for showing certain properties of derivatives. For example, as you can see, when sine of x has an extremum, cosine of x equals 0. This is because at a minimum or maximum, the slope goes from either negative to 0 to positive, or positive to 0 to negative. We will also see what zeros of the second derivative, called points of inflection, represent in the next part. If the first derivative of a function touches 0 but does not change sign, like this, then it is not an extremum but a point of inflection. In physics, the first derivative of function of position represents velocity, with standard units of meters per second. A negative velocity represents motion to the left, and a positive velocity represents motion to the right. The farther a velocity is from 0, the faster the particle is moving. Here's what a discontinuity in the first derivative looks like on a graph, and here's what it looks like regarding the motion of a particle. From now on, I'll show a vertical line where the derivative suddenly changes. It may be obvious in this example, but it will be harder to see the difference for later derivatives. Here's the second derivative of x to the 10th over 10 factorial, x to the 8th over 8 factorial. And here's the second derivative of sine x, negative sine x. The second derivative represents something called concavity. When the second derivative is positive, the graph is concave up, like a bowl, or a U shape. When the second derivative is negative, the graph is concave down, like a dome. Formally, concave up means that a tangent line will fall below the graph, and a line connecting 2 points on the graph will overestimate it. Concave down means that a tangent line will lie above the graph, and a line connecting 2 points will lie below. These are sometimes called convex instead of concave up, and concave instead of concave down. In basic geometry, convex shapes are shapes where a straight line connecting 2 points on the shape will be entirely within the shape, and concave shapes are shapes where it is possible to draw such a line that leaves the shape. For sections of the graph that are convex or concave up, you can imagine pouring water onto the graph and it will form a convex shape. As soon as this water level gets above the points of inflection, where the second derivative changes sign and the graph changes concavity, the shape the water forms will become concave. The points of inflection on sine of x happen to also be its zeros, but these can be any point where the second derivative changes sign from negative to positive or positive to negative. This may still look like a convex shape, but if you zoom in very close to the graph, you can see that this line, which connects 2 points on the boundary, goes below the shape. In physics, the second derivative represents acceleration. How fast is the particle getting faster? How fast is its velocity changing? This is given in meters per second, which is usually shortened to meters per second squared. Think of pushing on the gas pedal. Objects in free fall will also have a constant acceleration, which means if you throw an object, you can represent its path with a downward parabola, a negative multiple of x squared. A discontinuity in the second derivative looks like this. It might look subtle, but on a bigger scale, you can see that it goes from a line to e to the x. Motion along this graph looks like this. The third derivative of x to the 10th over 10 factorial is x to the 7th over 7 factorial. The third derivative of sine of x is negative cosine of x. It is here where derivatives start to become a little more obscure. You'll hardly see the third derivative in a calculus or physics class. I'll go faster from here and just show the examples and maybe some fun facts. Keeping in mind that a polynomial with degree n, meaning x to the n is its highest power, has n derivatives that aren't 0, here are the graphs of x to the 0 through x to the 100 excluding odd powers. As you can see, the higher the power is, the less it changes. Anything after 20 is basically vertical. The difference between having a fourth and sixth derivative is already negligible for most purposes. One application I found for the third derivative is something called torsion. I'm not going to explain it fully, but a formula used to calculate it involves the third derivative. In physics, the third derivative of position is called jerk, and it's what you feel when you start going up in an elevator or rising in a plane as your acceleration changes from the acceleration of gravity to something higher. It is given in standard units of meters per second cubed. Here's what discontinuous jerk looks like on a graph, and here it is zoomed out with the x-axis stretched out so you can really see the difference. Here's the motion of a particle with discontinuous jerk. For odd derivatives, this motion may start from right to left, reflecting the decreasing graph, but only when it passes the line from left to right does the derivative jump. The fourth derivative of x to the 10th over 10 factorial is x to the 6th over 6 factorial. The fourth derivative of sine x is sine x. We've finally come full circle. Now I'd like to show sine x as it passes through its derivatives just like a real wave. Here it is with derivatives in the background. It is because of this wave-like nature, where the slope slides from 0 to 1 and back, that sine of x goes through a cycle of derivatives. The fourth, fifth, and sixth derivatives of position in physics are typically called snap, crackle, and pop, and they're sometimes called jounce, flounce, and pounce. The fourth derivative of position is given in units of meters per second to the fourth. Railway designers try to minimize snap in tracks, which allows for linear radial acceleration, which is acceleration combined with a change in direction, or curving. Anyway, here's a function that is discontinuous in the fourth derivative, and here it is zoomed out. Here's the motion of a particle that has discontinuous snap. I'll probably go through the rest of the derivatives pretty quick, but don't worry, I have a surprise for you at the end. The fifth derivative of x to the 10th over 10 factorial is x to the 5th over 5 factorial. Since you've already seen all of the derivatives of sine of x, I'm no longer going to show them here. Crackle, the fifth derivative of position, is typically given in meters per second to the 5th. Here's a graph with discontinuous crackle, here it is zoomed out, and here's this motion with discontinuous crackle. The sixth derivative is x to the 4th over 4 factorial. Pop, the sixth derivative of position, is given in units of meters per second to the 6th. Here is a graph with discontinuous pop. Here it is zoomed out, and here's its motion. The seventh derivative is x to the 3rd over 3 factorial. The seventh derivative of position is called log and is in units of meters per second to the 7th. Here's a graph with discontinuous seventh derivative. Here it is zoomed out, and here is this motion. The eighth derivative is x squared over 2 factorial, which is really just x squared over 2. We're down to a simple parabola. The eighth derivative of position is called drop, given in units of meters per second to the 8th. Here's a graph with discontinuous drop. Here it is zoomed out, and here's this motion. The ninth derivative is just the graph y equals x, a straight diagonal line through the origin. The ninth derivative of y equals x to the 10th over 10 factorial changes at a constant rate. The ninth derivative of position is called shot, with units of meters per second to the 9th. Here's a graph with discontinuous shot. Here it is zoomed out, and here's its motion. Finally, we have reached the end of our derivatives. The final 10th derivative of x to the 10th over 10 factorial is the constant graph y equals 1. The 10th derivative is the same at every point on the graph. The 10th derivative of position is called put and is given in units of meters per second to the 10th. Here is a graph with discontinuous put, here it is zoomed out, and here's its motion. We're done with the main part of the video now. It may have seemed kind of pointless to go through these last few derivatives, but I find it helpful for understanding what taking derivatives really means to see a lot of examples, especially in order like this. Here's what all the derivatives look like on the screen at once, and I find it kind of beautiful. Here they are color-coded without the last two, and with x to the 10th over 10 factorial in red and x squared over 2 in magenta. Here is the same visual zoomed out with the x-axis stretched. As you can see, the order of colors has switched. On this scale, it becomes apparent that the later derivatives actually increase slower for values less than -1 or greater than 1. Here's what x to the n over n factorial looks like with n up to 100, going up by 2 at a time, so each graph is the second derivative of the next. To end off this video, I'll talk about the opposite of a derivative, an integral. An integral between two x values finds the area under a curve between these two values, but it can be calculated by taking the antiderivative or going backwards from the derivative. This equation is called the fundamental theorem of calculus and says that the integral from x equals a to x equals b of f of x is equivalent to the antiderivative of f of x at b minus the antiderivative of f of x at a. The integral of x to the 10th over 10 factorial is x to the 11th over 11 factorial. The integral of sine x is negative cosine x. The integral of position, or as I will now be calling it, displacement, is known as absolute, which is short for the absence of displacement. While the nth derivative of position was given in meters over seconds to the nth power, the nth integral of position is given in meters times seconds to the nth power. What does meters times seconds even mean? It can be thought of as the accumulation of displacement. If the displacement of a particle stays at the same positive value over a period of, say, 5 seconds, none of its derivatives will change. However, its absolute will increase as the area under the position curve increases. An intuitive way to imagine this is with a spring. If you pull one end of the spring out, the deformation of the spring will depend both on how far you pull it out and for how long. This strain on the spring can be calculated approximately using absolute. It also has some applications in fluid flow and modeling of human body structures. You can think about how the longer you hold up a weight, the more your arm hurts, and we could model that muscle pain with the absolute of the weight's position. I'll put a link to the Wikipedia of absolute in the description if you want to learn more. We can continue on in this pattern, taking higher and higher integrals of position, all of them some combination of the corresponding derivative and absence, velocity and abscity, acceleration and abceleration, jerk and abcirc, and so on. Unfortunately, most of those don't have many applications. Honestly, I just think it's so cool that with a relatively simple math system we can describe so many properties of motion. Anyway, we're at the end of the video now. If you made it this far, thank you so much for watching. I hope you learned something new about derivatives, even if you've already taken calculus, or maybe even got more interested in math. Please consider supporting 3 Blue 1 Brown, the creator of Summer of Math Exposition, the challenge this video is for. I'll leave a link to his channel and the information page for the contest in the description. The background music for this video was composed by my friend Peter, whose Bandcamp I will also link to. Thanks again for watching, and have a great day.